So let's say you have a cylinder with a small opening here, but a much larger opening over there. So necessarily, the area on the second, A2, and let me use maybe a different pen. So A2 would be equal to 10, whereas A1, or the beginning area over here, will be 1. And let's say the units are in centimeters. So 1 centimeter versus 10. And let's say a force is applied to this end about 10 newtons much. So about 10 newtons much of force is applied. Right, so F1 will be 10. If F1 is 10 and A1 is 1 centimeters, what's the pressure experienced by, let's say, a metal on here? So this metal, and there's also a metal over here, so let's call this M2. Or no, let's not call it M2 because that might be confusing. It was mass, which we might venture into in the same video. So what do you want to call this? The first piston and the second piston. So the first piston will experience a pressure. Now, this pressure, how would you find it? Well, the equation will be pressure is equal to force over area. Right. So what is the force we're applying? Well, the force we're applying would be 10 newtons. And what's the area? Well, the area, as we said, is 1 centimeter. I forgot a square here, but it's 1 centimeter squared actually. So 1 centimeter squared, which would be the pressure would be equal then to 10 centimeters, no, 10 newtons per centimeter squared. So since pressure is about how much force is being applied on a specific area, this will have a 10 Newton per centimeter squared pressure. Well, the water, we know, is going to be pushing. It's going to be pushing. Even when it's widening, the water will experience 10 newtons per centimeter squared here, but it will also experience the same over a larger volume of water over here as well. Let's say the dots represent about equal levels of pressure. As the water widens, more volume of water experiences the same level of pressure. Right? So over here, there'll be way more water, but they will all be, since it's a compressed liquid and energy is not lost and neither is pressure, they will all be experiencing the same level of force. So as we said earlier, this area of the piston will also experience the same level. It will be getting pushed by the water by 10 newtons per centimeter squared. But over here on the beginning, there's a much smaller area of only 1 centimeter. Whereas on the second piston, there's a much larger area, right? So 10 centimeters squared. So about 10 times larger. But it's experiencing the same pressure. But pressure, P1, is equal to P2. The pressure experienced by the second piston is the same as the pressure experienced by the first piston. Well, then something has to give, right? Because if pressure is equal to force over area, right? And, well, let's call this force 1, A1. And we know pressure 2 is also going to be equal to F2 over A2. And we just said the pressure is going to be the same, although A1 is about 10 times smaller than A2. Well, what does that tell us about F2? And this is a very common sense question. If this denominator, A1, is much smaller, and this denominator, A2, is much bigger, but the pressure or the value stays the same, that means necessarily that the force has to be much larger too between the two. So, and it is actually, because let's sub in the numbers. Force 1 is going to be equal to 10 newtons because that's our original force. applied over 1 centimeter squared. But since this is equal, right, because pressure is equal to F2, which we don't know yet, but we'll do some very simple algebra to find this. And A2, what's A2 equal to? What's the second area equal to? Well, as we said, is 10 centimeter squared. I know the numbers are getting all over the paper now, so I'll get fresh paper and we'll start over. But just remember the top, okay? Just hold that top, which is the pressure of 10 newtons. Oh, I guess I kind of forgot about my image, but from now on it will just be numbers. So 10 newtons will be equal to over 1 centimeter will be equal to a force, which we don't know the force 2, we still don't know, over A2. And what's A2? Just a reminder, is 10 centimeter squared. And you can go back on the video to see the diagram associated with it. So some simple algebra, we multiply this by 10 centimeters squared, so the denominator cancels out. And we do the same over here, 10 centimeters squared. So over here, the units will cancel out, because this is also a centimeter squared, and they are on the denominator and numerator. But the 10 will multiply this, so 10 by 10, and that will be 100 newtons, which would mean the second force, F2, is 100 newtons. And how much larger is 100 newtons compared to our initial force? This is a final force, which let's call it FF, and our initial force is 10 newtons. So how much larger is that? That's 10, because of the pressure rules. And this law is called Pascal's law, which states pressure is transmitted undiminished in an incompressible liquid. And this could be used in principles such as hydraulic jacks. Like this principle is used to create such machines as a hydraulic jack is what I meant to say. And when two pistons are being carried. So this helps you kind of apply your force over a larger distance. But we're going to see on the next video why this does not mean you get to create energy or destroy energy, or how this does not violate the rules of nature, let's say. Because initially you would think, wait, so I'm applying less force here, which is 10 newtons, and I'm getting a lot larger. I'm getting a tremendous return of force, because by applying 10 newtons here, you're moving this 100. Not moving this 100, sorry, that's a wrong expression. By inputting a force of 10 newtons on a smaller area, you're experiencing on the larger area a force 10 times larger. So that must mean energy was created. Wrong. It's not an infinity energy machine, and I'm going to explain that on the next video. Thank you for sticking around till the end of the video.